We continue from where we left off on the higher order linear ODEs with constant coefficients. In this case, I'm looking at examples on repeated roots. So I'm asked to find a general solution to the equation that. So I asked myself, what is the classification for this? It is a second order. It is homogeneous. It is of constant coefficient. So 1, -6, 9. It is a constant coefficient. And don't forget, this is linear as well. It is of the form yn plus p of xy plus some q of y equal to r of x, where r of x here is 0. So it is linear. As far as it's of constant coefficient, I can use the solution technique. I can use the root solution. So what do? I assume that the solutions of the form exponential, that I have to now differentiate this 2 times. So first derivative, I have that. Second derivative, I have this. Then I substitute into a differential equation. So y prime, I have to substitute into y prime minus 6y plus 9y equal to 0. So equation 1, equation 2, equation 3. Let's do the substitution. Alright. Now I can factorize. It means I can factorize lambda t out, and I have whatever is left. I divide through by e of t, and then I get this as my final. So this is the auxiliary equation. Or someone will say is the characteristics equation, depending on the book you are using. So I can go ahead and find my roots. You realize that this is lambda plus 3, lambda minus 3 all square. This is the only way to get lambda square minus 6 lambda plus 9. And so lambda 1 is equal to 3, lambda 2 is also equal to 3. It is 1, 2 because the highest order from the differential equation here is 2. It means I expect 2 solutions. Because the highest order here is 2, I expect 2 solutions. But they are all the same. So for the class of roots, it is repeated. So I can now write my final solution as C1 of the first lambda 3t plus C2t. So you remember here is t to the power 0, but we don't write that. E3t. And this is my final solution. Now let's take another example on the complex roots. Let me quickly go through my slides on the complex roots. Alright, so this is the first example. I'll take another sheet and then do that. We want to solve this problem. Let me change the ink here. Oh, this is not so good. Okay. Again, the classification here, it is linear. It is of the second order. It is homogeneous. And it is constant coefficient. I've explained how to get all these terms. It is linear because it is of the term this. So this is your q of x, this is your p of x, and that is the first number. Now, because it is this, I can use my root solution. I take the assumed solution of y equal to e lambda t. I differentiate this once, and then the second time. After doing the substitution, I can simplify. So I'll have it as substitute and simplify at a go. The more you do this, you get to see the pattern. It was going to be lambda square minus 6 lambda plus 25 is equal to 0. And this is what I have to find. So this is y, 25y. And I have to find the root for this. If I have to use a calculator or anything, I'm going to get the root to be negative 3. No, I'm sure it's going to be positive 3 plus or minus 4i. So since the highest order here is 2, it means that I'm expecting 2 answers. So lambda 1 and then 2 are this complex root. My real part is the a, which is 3. My imaginary part is the b, that is the 4. And so in writing out my solution, y of t becomes, it is of the form EAT C1 cos BT, and then the sign part. Now I realize that I'm not depending on the sign here. It is just the variable, the letter b, the value there, not the plus or minus, so that you don't get confused. A is 3, C1, B is 4, it is not negative 4, it is not plus 4, it is simply 4. So we are taking the values, not the signs attached to it. So this is how you find repeated root, complex root, as well as the real and distinct root. If and only if it is linear, it is a higher order, it means an order greater than 1, it is homogeneous, and then it has constant coefficient. That is the only way you can use the auxiliary equation approach. Please don't forget that. If it is linear, if it is homogeneous, it has constant coefficients, and then the order is greater than 1. So order 1, 2, 3, 4, 5. If this is satisfied, then I can use the roots approach or root solution. Please don't forget this. But if the order is equal to 1, then you simply go back to your first order differential equation, where it is separable, it is homogeneous. You can use the integrating factor. You can check if it is exact or non-exact. You can also check if it is nonlinear, like the Bernoulli. So you have to note the differences in the solution technique. Now in the next video, I'll take you through non-homogeneous with constant coefficients. See ya.